and thank you for tuning in. Welcome to a new episode of the Passion for Technology podcast by EBB Electronic.
Welcome to the Passion for Technology podcast. With the Internet of Things in Factory 4.0 applications, and especially in self-driving cars, more and more analog integrated circuits are being used. They enable digital systems to process signals from their surroundings. That means that they are increasingly being used in safety-related systems, such as in radar and LiDAR applications. To put it simply, if the signals were to be translated incorrectly, a self-driving car would likely end up in a ditch. Today we are talking to two guests about how to implement functionally safe systems with analog semiconductor elements and what the semiconductor industry is doing to help deliver reliable ICs. Michael Frese is the director of the Automotive System Functional Safety Department at Renesas. Hi, Michael.
Hello, Mustafa.
And Dr. Frank Galtier is the head of functional safety at NXP. Hi, Frank.
Hi.
Chips are performing more and more safety-critical functions in self-driving vehicles. Michael, what does that mean for the semiconductor industry?
Yeah, thank you for the question, Mustafa. So the semiconductor industry has to respond with adequate solutions. The chips which we develop, they need to be prepared to support the safety-critical functions in the most efficient way. This is a very crucial point here. And the solutions, they will have a lot of safety mechanisms integrated in the chips. And the chips need to be developed according to safety standards. So at Renesas, we started in 2007 with the first development of safety-critical products. These were MCUs, which were mainly required for electronic power steerings. And for self-driving cars, this, of course, becomes even more complex. So you have to consider the whole path, from the sensor data acquisition, the sensor processing, the sensor data fusion, and finally the actuations. And all functions in that chain are becoming safety related. And finally, the chips which are involved in that chain, they need to comply to functional safety standards like ISO 26262. So at Renesas, we have established processes for the development of mixed signal, analog and digital components. And these components are then developed according to the ISO 26262. And we'll have a set of work products which we can provide to our customers.
Frank, how can analog functions be integrated into safety-critical systems?
So as Michael said, when you build a system safety concept, you start from the safety goals and then you refine the safety goals into requirements at system level and then hardware level and software level and so on and so forth. And at the end, when you look at the hardware safety concept, the safety integrity level or the safety integrity, the requirement about the safety integrity will be also allocated to the different functions into the electronic. And then you will see, as Michael said, that not only the microprocessor or microcontroller will inherit this safety integrity level up to an ASIL-D, but also, let's say, the power supply, the gate drivers, the transceivers may also play a role. And this is the way analog functions and analog integrated circuits are also playing a key role into this system safety concept. I just give you an example, like for the microcontrollers, for instance, with the new technology node, we have the supply of the core it becomes lower and lower, like less than a volt, 0.8 volt, something like this. And with those new technology, you cannot anymore have a very optimized digital design as well as analog design in the same chip. So the only way is to define those analog functions outside of this microprocessor, microcontroller. And then this is the reason why we have power management IC, which is there to really supply the voltages to the different, not only to the micro, but also to the different other chips that we may have in the hardware design. And as we said before, those power supply, for instance, will also inherit the ASIL level up to an ASIL-D for some of the systems or some of the application. And this is how you come with ASIL-D requirements on a PMIC, as well as, let's say, ASIL-D requirements on a gate driver, for instance, or on the front end for radar or this kind of things. Not ASIL-D, but for radar, it's going to be more like ASIL-B today. But this is the reason why we got some safety requirements to analog functions as well.
Michael, what's necessary to achieve a level of functional safety that's required for ADAS, for example?
That's a very complex question, and I think we can talk for hours on that. Because ADAS is a very broad term, which has many functions. And let me try to give a short answer. So ADAS means SAE level 0 to level 2 for advanced driver assistance systems. So These systems are mainly fail-safe systems. Some of them are supporting functions and they are just QM. So the requirements can be significantly different. So we have, for example, automated emergency braking systems, which are rated with ASIL D, and we have automated lane keep assist systems, which are ASIL B. And the safety goals of these are completely different. And therefore, the safety architectures and requirements are also different. It means that the semiconductors, they have to consider from the system safety concept the different architectures and have to be prepared to support the safety requirements in a proper way. And there's also another trend, which is going to integration of functions into zone and server-based architectures. And for these systems, the SoC will provide the suitable safety mechanisms to support these functions. And the main point is also to have the safe operation and to enter in a safe or degraded mode when it comes to a failure. The SoCs, they will have, for example, an ASIL D safety island for doing the computation towards the actuation and making the decision. We will have redundant and diverse sensor data acquisition and processing. And there are application processors or hardware accelerators which even support up to ASIL B.
Frank, would you say that special chips are required for those purposes?
For sure, special chips are requested for this purpose. First of all, as Michael said, we have to develop safety-related chips, IC SoC, so it means we have to comply with the ISO 26262, and we do it only if it's requested, right? So if we would only need a QM part, then we would just develop a QM part, because developing a safety part means spending more time and more effort during the development, also more die size to include a lot of safety mechanisms inside, and so on and so forth. So there is clearly an impact on the development of the component and specific features in a sense of new functions. For sure, in autonomous driving, we are very much talking about artificial intelligence, because the big concern is that you have more and more sensors. As Michael said, you have to have heterogeneous concept with multiple type of sensors, radar, LiDAR, camera, and so on and so forth. And the amount of data that you have to compute becomes so huge that with traditional algorithms, there is no way to manage this huge amount of data. So the data crunching is so huge that you have to move to this using neural network and artificial intelligence to deal with this amount of data. So it means that new hardware accelerators have to be or new features have to be implemented into the SoC or into the ICs as well. But at the end, it's still the challenge how to make it safe, right? Not so simple. And we don't even talk about ASIL D, right? So this is really the new type of functions and features that we have to include into our component to target this autonomous driving.
What role do quality standards such as ISO 26262 and IEC 61508 play, Michael?
As mentioned already in the beginning, so compliance to ISO 26262 is a must for safety-critical automotive systems. The IEC 61508 was considered in the beginning when the ISO 26262 was not available. This is some years back. And nowadays we see requirements in the automotive area from all customers across the world regarding ISO 26262. And especially for control application like ADAS and AD systems, the standard is relevant. So Renesas has established an efficient process to mitigate systematic faults and develop the chips as safety element out of context. And the chips have a lot of integrated safety mechanisms to support the detection and mitigation of random hardware failures. So we are also providing a rich set of functional safety work products. These are the safety manuals, the safety requirement specification, safety analysis with the FMEDAs. These need to be customizable so that the customers can adopt the safety analysis according to their safety goals. And this helps the system integrator, the integration into the system.
So now we've talked about special chips, we talked about quality standards. Frank, can you elaborate a little more on what needs to be considered when designing analog ICs in order to create safe and reliable systems?
Okay, so it's pretty complex questions, I would say. And I could spend more than hours and hours to explain what we should do to develop an analog function to be ASIL compliant. So first of all, I think what Michael explained about the safety standard, this is one of the key things, right? This is the state of the art. So this is very good that we have such a standards like ISO 26262 for automotive and also IEC 61508 for industrial, because this is really defining the state of the art. So this is the first thing that you need to comply to, right? And then the beauty of these standards is that even if it's a little bit sometimes difficult to understand how you should apply it, and this is why there was this part 11 in the second edition of the ISO saying what you should do, how you should apply the ISO 26262 to semiconductor, because it was very much oriented on the OEMs and tier one development flow or V model, so as we can see in the standards. But at the end, as Michael said, we started with the IEC 61508, trying to navigate there where it's even worse with the 61508 to understand what you should do for an ASIC or for an ASSP, let's say for a semiconductor component. It was even more difficult to understand what you should do. With the 26262, it's a bit better. So the first thing is what you have to do is actually to comply with the standard. So as Michael said, there are multiple aspects which is really related to what we call systematic fault and systematic capability. So it means, do I develop a device which is free of bugs? And can I be fully sure that I've not missed anything during the development, or I've not introduced any bugs in the system or not discovered any bugs in my chip during the development? So it's really something that we have to manage during the development. And the ISO is focusing on this with some specific parts about, let's say, project management, configuration and change management, requirement management, this kind of things that we have to follow and fulfill. This really can be seen as very much process oriented, but this is true. And I do believe that half of the way is really development flow and process to avoid those systematic faults. And on the other side, we have for sure to define the proper safety architecture and safety concept. I mean, first the safety concept, and then the safety architecture that will fulfill this safety concept. And at the end, what is key is the verification. You need to verify what you have implemented, right? So you need to verify every step of the development. You need to confirm that your safety concept is actually fulfilling your requirements. And at the end, also fulfilling the requirements of the ISO 26262 in terms of hardware architectural metrics, which is the only way to have quantitative analysis and quantitative metrics about the safety architecture.
So how are semiconductor manufacturers helping designers in their work?
If you mean semiconductor manufacturers like NXP and Renesas, in the case supporting designers like hardware designers or system designers like from a tier one company, Bosch, Conti, and this kind of things. We mentioned the industrial with the 61508, and we mentioned the ISO 26262, which is a kind of, let's say, I would not call a derivative, but a dedicated standard coming from the 61508 for automotive. So what we have seen in the automotive is that there is a lot of responsibility given to the semiconductor manufacturer. As you can imagine, and as you know, we are, let's say, having a lot of safety function into the product, into the semiconductor component. We have microprocessor, power supply, gate drivers, transceivers, and so on, with different ASIL level like A, B, C, D. And in industrial, this is very much different. They are building the safety concept at the system level by having some kind of, let's say, dedicated architecture like multiplication or duplication, triplication, 1 out of 2, 2 out of 3, these kind of things. We don't have it so much in automotive. The goal was to integrate as much as possible in the semiconductor. Then to answer your question, I would say without semiconductor component like the one we are delivering today at NXP, I think it would be very much difficult to build any kind of system safety concept at the tier ones level or even OEMs. So we are helping very much the designers of tier ones company because most of the safety functions are actually inside the semiconductor component.
Michael, staying with the design process, do special or additional test methods need to be incorporated into the design process?
So as Frank already mentioned, so we have a huge amount of safety mechanisms implemented in our components. So these are the voltage monitors, temperature sensors, ECC on the memory or on the bus, logic or memory bits at startup, dual core lockstep CPUs, which really support the safety design of our customers. And there are also safety requirements or assumptions of use, which are external to the semiconductor components. And for the on-chip safety mechanisms, you need to do the verification during the design. And you have to apply specified operation and detection capabilities. So you have to execute basically a proper verification of the safety mechanisms by fault injection on different levels or doing the electrical characterization and production tests. And this is necessary to ensure that the safety mechanisms which are integrated function as specified and also that their failure reaction is exactly what you wanted to realize. So therefore, you have to do and apply these test methods to your design. But also for the system integrator, there are special tests required because if they integrate our component into their systems, they have to ensure that basically the failure reaction of the safety mechanisms is behaving as expected so that also their software or their secondary error path is really taking failure reaction correctly within their system.
In the highly connected vehicles of the future, functional safety will almost inevitably be linked to cybersecurity. Frank, what are implications of that?
So it's a very good topic, I would say, and very trendy topic, I would say, at the moment. So everybody's talking about safety and security. I remember some discussion where those guys said, hey guys, you do a safety product and you also do a security product. So you have in the same microprocessor or SoC, you have a secure element, a very complex safety concept. Why don't we use the same mechanisms? Because you see that there are some kind of similarities, at least if we just talk about safety mechanisms versus security mechanisms, right? I just give you an example. When you do a communication over any kind of bus, can be CAN, can be Ethernet, can be whatever, even let's say wireless one. So if you need to ensure the integrity of the data in terms of safety, you may have to add a CRC on top of the data, right? If you want to secure the communication, you may use the CMAC, right? So it's a kind of, I would say, pretty similar type of protection. And then for sure, the customer was asking the question, why don't we just use one instead of the two, right? So we need at the end to have, we increase some of the size of the payload just because we have to put a CMAC inside plus a CRC for safety. So it's a little bit stupid to have the two things. There is also the same story for, let's say, secure storage. When you want to secure the data in a memory, you want to be sure that the data is safe or the safety integrity of the data is ensured inside the memory when you keep the data in. And you also want to be sure that the data is encrypted, right? So you have multiple ways. You have, once again, like two mechanisms that you will have on top of each other to ensure safety and security. So everybody is thinking about, hey, how can we, let's say, be more efficient and then commonalize the things? The big challenge I see there is that safety is something which is, let's say, we monitor all along the life of the vehicle. That's right. So we build a safety concept that will be running in the field all along the lifetime of the vehicle. However, the safety concept is actually built during the development. So the safety concept, and it's somehow what I would call static, right? So we build a concept at the beginning, we analyze all the type of failure modes and what can happen and so on. We are exhaustive in this type of analysis. We build a concept, we put the concept in place, and then it goes into the field. For security, this is a little bit different. The dynamic is different. They are also building a concept at the beginning, but depending on what can happen on the market, a hacker is coming and finding, a way to attack your system, then you need to react, right? We need to react. We need to maybe make an upgrade. We need to make a software update or whatever that we can fight against the hackers. And this is very much more dynamic than for safety. If we would combine a safety concept with a security concept, would be a disaster after like 6 months or something like this. You would have to change the security concept and that would impact your safety concept because you would have to revisit the safety concept and it would be pretty difficult to do it quite quickly for an update in the field. However, as we see in NXP and also on the market, we can easily align the processes. And this is already done. The next step would be to understand to which extent we could commonalize security concept and safety concept.
We've drawn on self-driving cars as an example for an environment where ICs are needed that meet very high safety levels. Michael, what are other applications? What are other domains where you need ICs that meet similar safety levels?
There are a lot of automotive applications which require functional safety. So basically, all applications which could cause harm when they malfunction, basically. And these are applications which have an actuation, basically, which drive a motor or which display safety relevant information to the driver. And this starts then basically from the data acquisition, processing of the data towards the actuation. For this, meanwhile, almost all ICs have allocated safety requirements. And in Renesas, the majority of the products which we developed for automotive are developed according to ISO 26262. We have some legacy QM products for which we provide some supplementary information to support their use in a safety critical applications. And as we already touched in one of the previous questions, there is a trend which we see that functions are merged to zone and server-based architectures. So it means your actuators will become less intelligent and you move basically the intelligence to a centralized place. And then, as also Frank mentioned, you have to deal with the allocation of different ASIL onto one central zone or server-based architecture. And these applications, they will run then on these central zones and servers and provide their outputs to the less intelligent actuations. And all these functions require special safety considerations, and you have to install the safety mechanisms in the system in a most efficient way.
I would like to add something to what Michael said, and it's absolutely right what you said, Michael. I fully agree on this. We have autonomous driving on one side and we have electrification on the other side. And for the electrification, for sure, there is this motor drive with a lot of activities running in the background, trying to understand how we can make it, let's say, more available again. So it's really about availability, so increasing the availability of this. And actually at NXP, we are very much focusing on this electrification domain, but starting from the battery. We are very good in the battery management system at NXP. We have very good product. And then we are very much focusing on the complete energy conversion from the battery, 400 volt battery, up to the electrical motor. And also considering onboard charger, for instance, like when you want to, let's say, charge this plug-in hybrid vehicle or the full EV vehicle, a huge demand of functional safety product.
Looking into the future, do you think that it will become easier to implement functionally safe and reliable systems? And I'm also interested in both of your takes. Michael, let's start with you.
That's a very difficult question. So I would say yes and no. Yes, because in the semiconductor industry, we are already providing safety products since a long time. And these products, they have really a rich set of safety mechanisms, as Frank mentioned. So the system designers, they rely on the safety architectures and safety requirements and mechanisms which are implemented in the semiconductor products. And we provide our components along with the safety work products, which we mentioned before, safety application node, configurable FMEDAs. And furthermore, we are also providing on top software safety libraries, which abstract most of the low-level safety mechanisms. So basically, the customers can concentrate on their application development. On the other hand, I would say no, because the systems are becoming more and more complex. So functional safety as per ISO 26262 is not the only challenge which we have to consider. So for example, for self-driving cars, there's also the safety of intended functionality. And this is one of the most challenging items in the industry. Another difficulty or challenge I see is a trend towards artificial intelligence and machine learning. Artificial intelligence is more and more involved in safety critical tasks. And here the biggest challenge is to ensure really the safeness of AI, ML in future systems.
Frank, what's your take on it?
And thank you for your answer, Michael. I think I could not agree more. I mean, you said almost everything, right? So the only thing I would add is that the product itself, functional safety, you're absolutely right. We are today able to do multiple ASIL level in the same chip with very good argumentation and mechanisms to ensure the coexistence. Renesas as well as NXP, we have a long history in functional safety products. So we are able to do ASIL-D product. Delivering ASIL-D product is maybe not the biggest challenge, as you also said. Before we can reach this fail operational where maybe the solution will be like just duplication, triplication. As I said before, like the IC 61508 is actually promoting for industrial, because for autonomous driving, and it's also connected to what you said, Michael, about this SOTIF, the safety of the intended functionality. when you need to deal with some limitation and technology limitation of some sensors and so on, there is no other way than just duplicating and having a, let's say, heterogeneous set of sensors and maybe also duplicating actuators, right? So, but I think it's maybe not for tomorrow, maybe for the day after tomorrow. And until there, I think one of the key things that we will have to understand is how can we make, or how can we have in our ASICs or IC, SoC, how can we have mechanisms that will help the customer to reach a higher availability of the system. For me, higher availability of the system means I will not stop the system right after the first fault, is that I will engage in some degraded mode, or I will try to use this emergency operation that is defined in the ISO to really make a safe stop, but not in the middle of the road, right? So I see this availability as a big challenge. However, this availability is very much under the control of the tier ones and mostly driven by software. So as a semiconductor company, delivering also like low-level drivers, as Michael said, we are a little bit far from the application software, right? And sometimes those kind of degraded modes or degraded concepts are very like a secret sauce from the customers. And last but not least, one big challenge that we discussed just a little bit is that the ecosystem. Michael mentioned the software, libraries, documentation, safety manual, and so on. This is what everybody's called the ecosystem, right? How can we make the ecosystem much better so that we ease the integration of our component in the system safety concept? I think that's one of the key challenges that we have.
Moving from looking to the future a little more to the past, to the personal past, I'd love to know when and how you developed your individual passion for technology. Michael, let's start with you. When and how did you develop your passion for technology?
I think it started when being a child already. So I always liked to repair and fix things and look into technical details. I was always curious to understand how these items work and how issues can be solved. And for me, it was never a question what I will do in future. It always had to do with electronics. So in 1995, I started studying microelectronics. And for me, this was the future of any new technology. And looking back and comparing today's life against 1995, I think it turned out to be true that a lot of things have changed. And developing technologies which support and assist humans and to make their daily life easier is great for me. Even paired this now with functional safety, where we can reduce the risk of failures from electrical and electronic systems, becomes even more satisfying and fascinating. So technology which support humans will become safe, and it will protect lives when correctly applied. And this is always a great motivation for me. And yeah, I'm being proud to support the industry with our solutions.
Thank you, Michael. And Franck, what about your formative experiences? How did you develop your passion for technology?
Let me say that I think it was maybe by accident, to be honest. So to study electronics as well during the bachelor and so on. So I studied electronics mostly because my father was working in this area. So, when you are young, sometimes you are either you know already what you want to do like Michael, or you are more like me where you don't really know what to do. And then you said, oh, maybe I can do this. So I did it actually. And then finally, I started my first job as a designer, analog and mixed signal designer, and I enjoyed very much working in this environment. It was so exciting to see how much things you can integrate in a chip, right? I was very surprised that I liked this job from the first day. I also got a chance, by the way, to do a PhD, which was very, very, very interesting, honestly. This is where I started to understand that, let's say, analyzing the system as well as understanding what the system needs and then building or fulfilling those needs in designing a chip. I was really happy to do this, and it started to be really something very, very interesting to me. Moving to functional safety was a kind of, I would say, it came like a kind of a natural way, I would say. When I moved to automotive business, in automotive was really driving functional safety and drove functional safety very fast. Honestly, when you see where we are now from starting in 2007, 8, 6, 7, 8 with the IEC 61508 and where we stand right now in automotive and functional safety and safety in general. It's amazing how fast it moved, right? And I'm very happy to be a part of this adventure. As Michael said, I also feel grateful to some of things that we contribute to save some life, right? Or at least to make the road safer. I'm very happy with that. But I came to this by accident, and finally, I love it. It's great.
Thank you for sharing the origins of your passion for technology and tying it to the present and the future. Dear listeners, if you'd like to get in touch with either Michael Frese or Franck Gauthier, feel free to reach out via LinkedIn. You can find all relevant links in our show notes. Please feel free to subscribe to our podcast, Passion for Technology, on either Spotify, Apple Podcasts, or any of the other popular podcasting platforms. Thank you, Michael and Franck, for the insights that you've shared with us today and for joining our show. Thanks a lot.
Thank you too.
Thank you, Mustafa. Thank you, Michael.
Thank you, Franck.